Our goals for this video are twofold. We are going to see some examples using these limit rules, but we are also going to state some theorems at the end of this video for taking the limits of certain special kinds of functions. Let's compute this limit. And we'll start by observing that we have a sum and a difference. And one of our limit rules tells us how to take the limit of a sum and a difference. It's the sum or the difference of the limits. So one limit can break into three. Of 4x minus the limit as x approaches 2 of 1. Let's first take the easy limit, by which I mean this. The very first rule we have here says that the limit of a constant is just the constant. So this limit is 1. For now, we'll leave the first limit alone. And we'll leave the second limit alone. But this third limit is 1. Now, Rule 4 says that if we have the limit of a number times a function, we can just take that number and write it outside of the limit. And that's what we have both here and here. So our rule says we can take this 3 outside of the limit, and we can take this 4 outside the limit. See, double check this. 3 went out, 4 went out. All looks good. We have the limit of a power here. It was our 7th rule that says if we have the limit of a power, that's the power of the limit. So this is 3 times the limit as x approaches 2 of x squared. And let's leave this second limit alone for the time being. We're going to deal with this limit and this limit in the same way. The limit of the identity function can be computed by taking the limit and sticking it in there. So this is 3 times 2 squared plus 4 times 2 minus 1. And then that is whatever it is. 2 squared is 4 times 3 is 12 plus 8 is 20 minus 1 is 19. So notice we're taking the limit as x approaches 2 of this, and ultimately, what is this limit? It's gotten by putting a 2 here and a 2 here. So I've said, and this is certainly true, in fact, let me write it as part of the theorem. Ordinarily, if you're computing the limit as x approaches c of f of x, it doesn't matter what f of c is. In most cases where we compute the limit, f of c won't even exist. This theorem is an exception to that general rule. If p of x happens to be a polynomial, then we can compute the limit of p of x just by plugging c in. And we have something very similar to this for a second class of functions. Remember what a rational function is. A rational function is one polynomial divided by another. And if we're taking the limit of a rational function, then, assuming that it doesn't give us a division by 0 error, a limit of a quotient is the quotient of the limits. So, this should be the limit of this polynomial up here divided by the limit of this polynomial down here. And we've just said that we can take the limits of polynomials by taking C and plugging it in. So another theorem, if R of X is rational and R of C exists, the limit as X approaches C of R of X equals R of C. And you need this restriction because R of C might not exist. We might get division by 0 down here. In fact, when I was giving examples of limits that don't exist, one of those examples was the limit of a rational function. And I believe in particular this rational function. And if you try to use this theorem without any thought, you get a division by 0 error. So this theorem doesn't apply to every rational function. We have this extra condition. As a side note, by the way, still related to this theorem though, the limit as X approaches 0 of X divided by X exists and equals 1. That's because if X is not equal to 0, X over X is just the constant 1. And if you're taking the limit as X approaches 0, you don't care what happens at 0 itself. We cannot stress that enough. So here you're just taking the limit of the constant function 1, and it's 1. What this is intended to illustrate is that the limit of a rational function might still exist, even if we can't use this theorem. We can't use this theorem here. We get 0 over 0, but the limit does still exist. We have a trick for computing limits of rational functions when we can't use this theorem that we'll state towards the end of this section.